Thank you very much. Welcome, everybody. My talk will be on facial signals in affect analysis. And affect, the way I use it here, means emotional expressions. And I hope you will find a lot of links to what Danielle has been talking about, but also what Fernanda has been talking about. This is Istanbul. I'm just putting this up because we discussed yesterday that Istanbul kind of looks like Vigo because it has these two sides. And this is how Istanbul looks like from my university campus. So you see it's not very far from what we have here in Vigo. Okay. Now, in pattern recognition, faces should be considered as special objects, right? Because faces are very informative, but they have also some properties that separate them from other objects. Now, Fernanda has given you a lot of techniques, basically, to do pattern recognition, projections, etc. But all these techniques are generic techniques. I want to first motivate you in the way that we should treat faces in a little bit of a special way. Because humans are face experts. When we look at faces, we can read a lot of information into faces. And we have specialized hardware to deal with faces. But obviously, since faces reveal identity and also expressions, they are very useful for multimedia. So if you have if you're doing retrieval, etc. So who is Buffy, who is Willow in these footages? These kind of things can give you leverage in multimedia retrieval. But also, when humans look at this problem, they can be much more specific than computers. So you can, for instance, if you look at it, you can tell me whether Buffy is smiling at Willow in a sarcastic way or in a natural way. So these are things that is very difficult to implement with computers, primarily because facial expressions can be really subtle. So if treated as a pattern recognition problem, we have a situation where the levels of noise are almost always higher than the levels of the cue that you're searching for. So I'm going to first start basically with a disclaimer. Who here knows the Kuleshov effect? Okay, maybe you have seen Alfred Hitchcock talk about this somewhere because he used to know about this and he used to use it a lot. Now, Kuleshov in the 1920s did an experiment. He showed a number of people footages from small movies. And these are not the original footages, by the way. I couldn't find the originals, but they are representative enough. So he showed his subjects the face of a famous actor, famous back then, and it was a neutral face for a few seconds, and then a bowl of hot soup. Other subjects received the same facial expression, well, no, not an expression, it's a neutral face, but same footage of the person, and then they were seeing a girl in a glass coffin. And the third group of subjects saw the same expression, and then they saw a little girl playing with a teddy bear. Now, when asked about the expression in the face of this actor, the subjects all said that this actor was a superb actor, and he depicted hunger perfectly, or he depicted sadness perfectly, or he depicted sentimentality for the kid perfectly. You see what happens here. We read a lot into facial expressions. It was a neutral face. There was no expression in it. But we, as humans, use context a lot. And the problem in facial expression research is that our benchmark is not a qualitative result. Like, nobody cares what's the percentage of your classification on the Canada dataset. The benchmark is the human. Can you do classification like a human does? But this is a very difficult problem for this reason, because we use a lot of semantic information, a lot of contextual information, and we're also capable of reading things that are even not there. So I want you to take everything that I will be saying with a grain of salt. Okay, we will be dealing with a delicate problem, and pattern recognition is like a hammer. Okay, so we're going to be smashing it, but it's not going to be as effective as we want it to be. So this is my outline. I will talk a little bit about facial affect and emotions in general, and then I'm going to talk about face processing in humans and in computers, because facial expression analysis uses almost the same pipeline with face recognition. So if you have been doing how many people have ever worked on face problems? Okay, not many people, but still. So face recognition, I'm sure you have read at least a few papers on that. So face recognition is as a generic approach of analyzing faces is very similar to face processing for expression. So I will basically talk about this generic pipeline. And then, well, Takeo Kanada apparently, I didn't know that, but he apparently found that registration is the most important problem. He found this out 30 years before I did, but I also stumbled upon this. So I implemented for my PhD a face recognition pipeline, and the registration was the problem. So basically, I will talk a lot about landmarking and registering faces. And then I'm going to give you some examples and applications on how you can use these things in classifying facial effect. So let me give you a single overview slide just to put everything that I'm going to say next in a context. This is like a pipeline for facial expression analysis. Here you have a neutral face. Okay, you have taken an image of this neutral face. On this neutral face, you have illumination, pose, resolution, scale effects, changing the pattern that is the face. But also you have some emotion and affective influences, context, communicative intent, cultural influences, and other facial activities. So if this person is speaking, that's also deforming the face. So you get an expressive face. Okay, now we want to analyze this face. First, we start with data acquisition. Typical pattern recognition problem. We can use single images, we can use videos, we can acquire 3D, we can look at it with a Kinect. Okay? So there will be different sensors to record this information. Then we will do some pre-processing, especially if you're in 3D, for instance, you will need to eliminate depth artifacts and noise, etc. Then we do our face detection. Okay, who knows here what the Viola-Jones algorithm is? Okay, much better. So we're going to do our face detection here as rapidly as possible. But of course, we will be sensitive to poses. The Viola-Jones will not give us consistent cropping, so we will have some problems here as well. But then we will move on to localizing facial features. Because if we're going to do expression analysis, we will be needing what's going on in different parts of the face. So we're going to localize the eye corners, the nose tip, the mouth corners, and then maybe we will fit a model on the face and do some deformation analysis. Okay. Now, to help us in our deformation analysis, we may have some average face models indicating what a neutral face should look like or what an expressive face should look like. Then we will have issues like, do we have dynamic information, static information? What kind of expression are we looking for? Are we classifying spontaneous versus posed expressions? But then we also have here a whole bunch of processing ideas coming from the classification and machine learning literature. We can have fusion, feature level, decision level. We can bring in other modalities like gestures, sound, etc. And then we decide on the expression. So that's the generic expression processing pipeline. Okay? Any questions so far? Okay. So let me start with facial effect and emotions. This is my son when he was 2 weeks old. We were living in Amsterdam back then, and when he was born, the Dutch government said, okay, you need to make a residence permit for him. We said, okay, we'll go and take a picture from him. But the Dutch government wants a biometric photograph, which means he has to have a neutral face expression. So we took him to the, and by the way, you have to keep him like that because he's not able to, of course, sit at that age. What we discovered was that it was very, very difficult to get a neutral face image from a baby. And in the end, the guy made a series of photographs, and we took the one that looked most neutral and sent it to the to the IND. But when you look at these images, you can read actually a lot of emotions into this face, right? You can say, oh, he's kind of contemplating something. Now he's disbelieving me, you know. No way this is true. Why this happens is you are basically trained to read expressions, okay? Now you can see facial expressions in the simplest of patterns. And if you do classification on these, you will find expressions, you know. I will be presenting you several systems for facial expression analysis. If we put in one of these expressions, it will say contempt or sadness or happiness. The emotion will not be there. Okay, so we have to make a distinction between the emotion and the expression elicited by that emotion. It's not the same thing, right? So what is our motivation? Why do we want to do emotional expression recognition? Well, for artificial intelligence, obviously. I mean, you have all heard of Watson, who won the Jeopardy contest, IBM's computer. It knows a lot of... Who knows here Watson, by the way? Not many. Okay. So Watson basically is a computer that won $1 million in the Jeopardy contest. So the guy was asking Watson questions, and Watson was answering those questions. And it wasn't connected to the internet. So it basically decoded natural language queries, and it was doing a fairly well job of it. But Watson is a poor dinner companion, because it will not be able to respond to you in a social manner. So all Daniel's talk was about how to decode and understand social signals. And if we want to, you know, make a little bit of progress in AI, eventually we will be dealing with social signals. And face is like a, you know, a big source of social signals. Effective computing was a term introduced by Rosalind Picard, is basically endowing the computer with ways of analyzing and expressing emotions. That's also very relevant. And then you have a lot of application areas, like in human-computer interaction, you can have better interaction. In ambient intelligence, you can have smarter environments, you know, detecting whenever you're in pain, for instance. In cognitive sciences, you can provide tools for psychologists and cognitive scientists to actually analyze a lot of input. So at the moment, if you're doing psychology and mimicry, for instance, what happens is you hire a fax coder, and that person annotates manually a lot of video footage, and that's very expensive. So if you can give these people tools to do this automatically, you will be saving them a lot of time and money. Education, for instance, now there's a big aim of providing education to the masses over the internet. But all these systems are very non-responsive. They can't track whether a student is bored or attentive, etc. So if you can add some facial analysis to these systems, it can be very useful. More engaging games. In Europe, the gaming sector is now almost as big as the automotive sector. So gaming is a big future research area. Well, it's not a future, it's a big research area still. And some of these technologies we do have. Cameras that click when everybody smiles, we do have this already. So computational photography is one application area. So let's define the emotion then. Emotion is any mental state where full-blown or underlying might reasonably be considered to play a central role. Historically, it was Descartes who claimed that a few basic emotions are influential in our everyday lives. They're very salient. And those ideas got translated into Ekman's research, and so that's how us computer scientists mostly know about these. But there were also a few other influential people who thought about emotions. Darwin, for instance, said emotions are good for your survival. So fear and anger, for instance, should be classified much more rapidly by humans. So when we look at the human brain, we see traces of evolutionary optimization in the way the emotions are processed, but also in the way emotions are expressed. So if we want to treat emotional expressions as a special kind of pattern recognition problem, we might want to transfer ideas from cognitive sciences, from psychology to these domains. William James, as he expressed opinion about every major psychological theory, also specified some benchmarks for emotions. He said, well, we define fear, for instance, by saying fear is, when you're fearful, what happens is that you have adrenaline level that are heightened, you start sweating, etc. We call this fear, but it should be thought of the other way around. All these somatic changes in your body, this is what we call fear, and fear does not cause adrenaline changes. It is what we call actually fear. It's this adrenaline change. So he kind of coupled this more in an embodied way. So if you want to do expression, let's say with robotics or with embodied cognitive models, then you might be interested in thinking in a more integrative way, because the emotion there serves a purpose, and it should also serve a purpose in your system. So there are a couple of emotion theories that have been very influential. One of them is the circumplex model by Russell, and where he postulated that there are two dimensions that are very relevant for emotional expressions. One of them is valence, the other one is arousal. Valence basically tells you whether an emotion is positive or negative. So here you have happy, satisfied, content, etc. But here you have depressed, frustrated, sad, and gloomy. So this is the valence. The other axis is the arousal axis, which is kind of like the activation level of the emotion. And here, if it's a very low arousal emotion, you have drowsy, sleepy, tired, etc. And here you have aroused, excited, tense. Now this is a little bit different than the basic facial expressions. But we are actually capable of recognizing all these emotional expressions from faces. So these are all relevant for this kind of research. An important set of axioms came from Ortony, Clore, and Collins, which is known as the OCC model, and they have rather classified emotions from a perspective of agents. Okay, so what does that mean? Like you have some events that can cause some consequences, like something happens and I'm pleased or displeased as a result of that event. And then there are actions of agents that can cause some emotional expressions, pride and anger. And also there are some aspects of objects. There is an object, I can like it or dislike it, and that can be reflected in my emotional state. Nico Freide, who is, I think, still an emeritus at the University of Amsterdam, he took another stance. He said, okay, what kind of actions are elicited by emotions? So let's say you have an emotion of desire. What kind of action does it elicit? Well, it elicits an approach action, and its function is permitting consummatory behavior. So linking the behavior of a system to its emotional state is crucial, because the emotional state is conducive to the behavior, or it gives a communicational intent of how this behavior should be implemented. For instance, your smile is, let's say, it shows that the approach is possible, so it makes you more approachable. So if you want to do, let's say, an analysis and synthesis system on a robot, you should observe these rules, because those are the signals you will be giving to the humans who want to interact with the robot. Okay. There is a large group at the University of Geneva. Klaus Scherer works on that he has developed his own emotion theory. And it's kind of a little bit more complex than the circumplex model. There you have also high power and low power of emotional expressions, allowing you to control, and also obstructive and conducive type of distinction. So all these taxonomies, why do we do these taxonomies? Because one thing we want to do is we want to go beyond Ekman. We want to go beyond these 6 expressions that people try to, analyze for a very long time now. We want to do valenced and dimensional recognition of emotions. For that, we need a sound theory. We need to understand what is the space of emotions. What is the embedding, let's say? How do we project the cues that we obtain from people onto a space of emotions? There are also some emotions are not one-shot things. They have temporal aspects, which we newly start to explore through video analysis, for instance, or temporal analysis. For cognitive appraisal is the first stage. Events that have significance for our goals, concerns, values, they elicit emotion. But then we have subjective feelings about what's going on around us. And the appraisal is accompanied by those subjective feelings. Then there is some physiological arousal. Emotions are accompanied by autonomic nervous system activity. So if I want to do, let's say, facial expression research, but I don't want people to label the expressions manually, I can look at your physiological signals. I can measure your heart rate, or I can use an EEG kit to look at your brain while you're expressing the emotion and try to get the ground truth from a much deeper place, right? Then you have the behavioral aspects. You exhibit a certain behavior. But then again, here you have all sorts of cultural influences, in the West and in the East, emotional expressions may have different ways of expression. And finally, you have action tendencies. Emotions do carry behavioral intentions. When I smile at someone, that is not a random act. It may carry a communicative or intentional meaning. So when we're measuring emotions, then we don't do everything in this whole rich emotional world. We do some simplifying assumptions. We assume that emotions are on or off at any point in time. That means we say, okay, this guy is smiling, he's happy. We don't say, well, he's 80% happy but 20% disgusted. This kind of analysis is very difficult for us computer scientists, as getting our ground truth. So we assume that every segment has let's say, has a single label. Then we also assume that emotion is a state that the subject does not try to actively change or alleviate. So, for instance, I let you watch a funny movie, I record you while I do that, and you smile or you laugh. And then I record you and I say, okay, I have a database of spontaneous smiles. I assume that you did not smile or laugh just to make the experimenters happy. Okay, this is a simplifying assumption. But you will see that one of the biggest problems is collecting data in emotional expression research. Emotion is not affected by situation or context. That's one of our biggest assumptions because we collect our databases in a lab environment. And we assume that the lab is some place where people can be happy. It is a kind of like a weird assumption. We assume that emotions do occur in asynchronous communication. So we usually record people not in natural conversations, but in scripted settings, which is also kind of simplifying an assumption. And interpersonal emotions do arise from communication with strangers. The stranger in case is usually the experimenter, okay, trying to elicit some emotion. Now, if you want to categorize emotions, and if you say, let's use this arousal and valence kind of annotations, well, there are actually many more than the 6 basic expressions. Wiesel and Plutchik's effective dictionary contains about 150 emotional words. And you can say you know, you can set your benchmark really high. You can say, I'm going to implement a computer system that recognizes each and every one of these emotional expressions. Then you need to find a database that will have ground truth like aesthetic, elated, embarrassed, empty. You know, some of these are semantically quite challenging, right? And needless to say, some cultures have emotions that do not exist in other cultures. For instance, amae is a Japanese concept, I'm told, that doesn't exist in the Western culture. Or aksidie is a medieval concept which doesn't exist anymore. Sinful lethargy. We don't have a word for that anymore. It used to be an emotional state, right? So this is a very subjective, culture-driven labeling of, let's say, our emotional states. So we don't expect that a computer will be, you know, perfectly classifying all these things. Here's another representation. This time not in a two-dimensional space, but in a in a wheel-like. So when you start here, you end up here again when you do this. This is Plutchik's emotion wheel. The topology of the emotion space is also an unknown. And people cannot agree on a single representation for these emotions. So if I go back a few slides, okay. Now, this study puts emotions in a certain proximity by analyzing emotional words and their co-occurrences. But who says that for me personally, let's say, happy and satisfied are close emotions? Maybe I'm the kind of person that grumbles when he's happy, you know. Can be different things. So, to cut a long story short, what are the issues relevant for computer science? Well, we first need to define the emotions in order to be able to classify them. There is no agreement on basic universal emotions. We talked about the basic emotions a little bit in the previous talks, but there's still no consensus. Evolution versus culture, cultural aspects, and the emphasis is always on full-blown emotions. Nobody tries to collect database where you have, you know, half a smile, a little bit of fearful, because usually you need the full-blown emotions so that the effect is emphasized, right? So that classification can actually succeed. Pure emotions are very difficult to study. So if you are collecting a database, are you going to make your subjects really, really sad? How are you going to do that? Or really fearful, you know, really scare them to death? So these are very difficult to study. Ecological validity means you need to go into the natural setting where the emotion occurs in order to get really useful data. Deception is an important thing. Some people, especially actors, are very good at deceiving you. They can mimic expressions. They can create believable but fake emotional expressions. So who has seen this series Lie to Me? Okay, Lie to Me is based on Ekman. There is a psychologist who is assisting FBI, and they can detect, for instance, when a person is lying or not by subtle facial cues. You can do that in some cases, but there can always be deception. You can always, you know, very good actors have a lot of mastery over their facial muscles. And this is one of the things that make them masters, right? They know how to control their expressions, and they know exactly when to exhibit what expression. So they are masters of social signal processing, basically, and synthesis. Not emotions are equal. That means in your daily life, you show happiness much more than you show the other 5 expressions. You smile much more than you frown, for instance. And some people have proposed that happiness should be one class, all the other emotions should be another class, and then they should diverge. That's if you're doing Bayesian modeling, well, the prior probability is different for all emotions. That's what you should know. And then when you're evaluating emotions, when you have collected your database, somebody needs to annotate it, right? Then you need inter-observer agreement. So you have to say, let's say, 2 to 8 people annotate your database, and all should say, this is happiness, or a majority. And usually, good databases measure this by inter-rater agreement. We find some of the distinctions between emotions, or some of the commonalities in emotional expressions, also in the brain circuitry. For instance, selective impairment of emotional perception due to lesions is extremely rare. That means there is probably a single brain area, or let's say a few areas in the brain that process emotional expressions. So you don't have one area for happiness and another area for sadness, because if I damage your sadness area, then you would do well in recognizing happiness expressions, but not well in sadness expressions. Since this is extremely rare, we can deduce that there is some sort of common circuitry. However, there is differences in brain activity, like fear and anger are processed faster, and the prefrontal cortex is more active for anger as opposed to sadness, for instance. Can you guess why this is the case? What's in the prefrontal cortex? Anybody knows? Your motor areas, right? So if you're angry, you have a tendency to act on it. So if you're confronting a really angry person, there's a high probability that person is pretty impulsive with its actions at the moment, because this is the area that processes anger. Sadness and disgust have subtler representations as opposed to happiness and fear. It may have some evolutionary reasons why this is the case, but it poses tremendous challenges for us computer scientists, because we also want to differentiate between these emotional expressions. And then there are a lot of subcategories. You have a surprise, but you can have a fearful surprise or a pleasant surprise. So we have to distinguish between categories. Some further issues: interpretation accuracy. We need to interpret emotions. Then we also measure how good our assessment is. Since we're dealing with temporal things, emotional expressions have temporal nature, we have to set a window size, right? How long are we going, is our segment going to be? Are we analyzing emotional expressions in chunks of 1 second, 2 seconds, 5 seconds, right? So this has an important consequence for the models that you're dealing with. How are we going to measure the intensity? For instance, for healthcare applications, you may have, let's say, a pain detection algorithm. You try to detect the pain of your patient, and then you have to also measure the intensity of the pain. Is it a very strong pain? Is it a low pain? And people, have different tendencies of expressing their emotions. Usually when we measure an emotional expression, when we do classification, we compare the emotional expression with a neutral face, right? You have an expressive face, you compare it with the neutral face, and you say, look, the mouth corners have moved upwards. That must be a smile. So you need a baseline. If I give you a single image with a smiling person, how are you going to understand that the mouth corners are up? Maybe the person's face is like that, And as we get older, actually, some of the expressions that we do in our lives get ingrained, Our faces acquire those qualities. We have wrinkles specifically formed at the places where our frequent emotional displays are happening. And that's a problem, right? It becomes difficult to separate those wrinkles from wrinkles that happen during an emotional expression, especially if you're dealing with a single image. Generalization capabilities, we work with limited databases. How can we generalize beyond these databases? Modality fusion means if I give you voice or sound next to the image or video, would you be able to use it, for instance? If you're detecting happiness, for instance, Wouldn't audio be very useful? There are also other cues that can help you, shoulder movements, for instance, can also help a lot in distinguishing emotional expressions. Then, of course, treat it as a pattern recognition problem. You have to choose your learning techniques, your classifiers in the end, and set some measures. We come to Ekman's basic facial expression categories: happiness, surprise, sadness, fear, anger, and disgust. Sometimes this list also includes contempt, which is also a generic emotional category. Now, these are the most frequently researched emotional expressions, but a lot of variation. Okay, these are smiles from a single subject, and you see there are a lot of variations. Some of them show teeth, some of them do not show teeth. And as a pattern recognition problem, here you have a vastly different set of pixels, right? So you know immediately that this is going to be causing problem. Now, if you have a lot of training data, maybe that's not a big deal. But if you have single image per subject, then there are some things that you need to take into account in modeling all these variations. Also, some recent studies do contest that these are culturally universal. So Jack's recent paper in PNAS claims that there are significant cultural differences in understanding and expressing emotions. What they did was they randomly generated emotional expressions with a tool that they have developed, and then they took 30 subjects, 15 Caucasians, Westerners, and 15 East Asians, and all these subjects evaluated 4,800 such emotional displays. Something, disgust and medium. So they evaluated the emotion and the intensity. And here is the confusion matrix, so to speak. The Western Caucasian versus East Asian. Okay, happy, surprised, fear, disgust, anger, and sad are mostly well classified in the Westerners, but with a lot of errors, with a lot of different opinions, let's say, not errors. But if you look at the East Asian classifications, okay, that's, those categories are not as pronounced. Especially in some of these categories, you have a lot of overlaps. That says, are these really universally recognizable? Because if they are, what we're expecting is clear boxes here and nothing else, if everybody is able to classify those emotions unambiguously. So Ekman's studies are very nice, very thorough. This is just one paper that objects to it, so it should be taken with a grain of salt until these are replicated many more times. But there is still, the question of the categories of emotion is still not resolved. And this actually kind of supports the dimensional models of emotion. Instead of discrete categories, we have a continuum. Not just a line, a continuum in a higher dimensional space, right? An embedding, if you want. Now, okay, these are all from static images, but, well, no, these were videos, but we have time and again seen in the literature that facial movement is very informative for classifying expressions. Now, Ekman says that the apex of the emotion, the peak of the emotion, is like a summary for the emotion, right? The moment where your smile is at its height can be used to recognize your smile. But if you look at the temporal unfolding, that's also very informative. And people have came up with schemes to encode this. Now, the facial definition parameters, the facial animation parameters in the MPEG-4 standard is one such encoding scheme. But the facial action units of Ekman and Friesen is another such scheme. And since Fernando talked about these a little bit, I'm not going to spend too much time on it. Basically, you have all the muscle movements of the face are quantified in these action units. So if you do something with your face, theoretically, I can encode it in action units. Not just one, a combination of several, probably. And they all have an intensity scale from 1 to 5. And you need to get a certificate to be able to annotate this officially. So, but here you see the examples from the Bosphorus database for the lower action units, and for the upper action units, which we have less of. So we have more control over our lower face. And then you have some combined action units that always occur together. Well, not always, but they do occur together, and they have a, let's say, a tendency to occurring together, so they are classified as separate action units. And then you have these 6 basic emotional expressions. That's the MFAX coding in Ekman's terms. Any questions so far? Okay. Who has ever collected affective data here? Very few. What kind of modalities? What were you using?
Video
and for basic emotions?
Yeah, mostly, but it was in a realistic setting. So.
Okay. What about you?
Also video and that they were for product.
Prototyping.
Yes.
Mm-hmm. Ah, okay, product appreciation, yes. Who has worked with faces before? Did I ask this? Yes. Okay. Well, when you're doing effective data collection, there are, well, the protocol is like the most important thing. You have to make sure that it's fixed beforehand, and it's fixed in a way that will allow your analysis in an unambiguous way. But the most expensive part is not the data collection itself, it's the annotation. Right? We have collected a database, I'm going to give you the details of it, in 5 weeks, and then the annotation took us 6 months. So that's the kind of scale that usually takes about 5 to 10 times more annotation. What you should be careful about is whether, if it's an emotional expression, is it spontaneous or posed? That's the first thing that you need to distinguish. Is the emotion elicited by an external situation, or is the subject asked to create this emotion for you? And then if it's the second one, it's better to use professionals for this, because if you ask random people from the street to give you disgust, let's say, and then to give you sadness, you will probably not be able to tell the difference, because they wouldn't know how to pose for disgust. In a real setting, they might show it correctly, but if you ask them to do it, they might not succeed. So the setting also is important, because the setting influences your perception, your body, and the response of your face is strongly conditioned on that. And then you need to kind of check for the feelings, right? Is the emphasis on the external expression? Are you being a complete behavioralist? Or are you also paying attention on the internal feelings? And then maybe you do questionnaires to validate the emotions. Well, is the subject aware of the recording is an important issue. Unfortunately, the ethic committees usually do not allow you to record people without their explicit notice. I'm not sure. It depends from country to country. In Turkey, our ethics committees are a little bit more lax, but in the Netherlands, I know they're very strict. So this is something that you need to take care of, and you need to let them sign agreement forms, etc. So that's something you should be careful about. And then the subject, what does the subject know about? That's also very important. So if you're reading psychology papers, I know some of you have psychology background, the experimental setup needs to be specified in great detail so that other people first can replicate this experiment, and then maybe other people can find their correlations and influences that you haven't thought about. Okay? You recorded all your recordings in Vigo at 12 o'clock, and all your subjects were hungry. And that shows in the database. Their mouths are salivating, etc. Or you recorded your data after the lunch, And then everybody is drowsy, everybody wants to sleep. That's also visible in the facial expressions. Okay, so if you're doing data collection, I can probably do a two-means clustering and tell which subjects have been recorded before lunch and which subjects have been recorded after lunch. So these things you should be careful about. I put here a few databases. If you want to do research on facial emotional expressions, well, Danielle sent you a PDF, so I'm going to skip this. It's in the PDF, the database, the details, the location of the database, and then you will also find a couple of tools useful for starting, like toolboxes, etc., to start you on your research. Some of the newer databases after the publication of this chapter, the Con-Canada dataset was extended in 2010, and the examples Fernando showed were from the extended Con-Canada database. And then there is a more recent database which encodes 3D facial action units. So this is also interesting. Any questions so far? Okay. I'm now going to talk about something which is very generic. So it doesn't relate to expressions much. It's about face processing in humans. Who knows some things about face processing in humans? Anybody who has read anything in psychology literature about this? Do you know why faces are special? Okay. Maybe this will be interesting for you. So the first question that psychologists ask is face recognition different than object recognition? Or is it just another recognition problem? And they had a couple of things to suggest that face recognition is special. First of all, they did some fMRI measurements in people who are looking at faces and then looking at objects. And they can show that faces activate certain parts of the brain. Canwisher and his group labeled the fusiform gyrus the fusiform face area because of that. Because whenever you're processing a face, that area has a lot of activation. So it's doing something relevant for face processing. But there were also other cues. For instance, in prosopagnosia, people lose the ability to recall faces, to recognize faces. But in agnosia, you can't recall objects' names, but your face recognition is intact. So this is something called double dissociation in psychology literature. It indicates that two separate modules are actually doing the processing because they can get selectively impaired. I can impair either this or that. That means there are two of them. In prosopamnesia, you cannot learn new faces. This is kind of like a variation on a theme. And in the Capgras syndrome, you do recognize faces, but you lose the familiarity sensation that is associated with faces. So you see your mother, you say, well, this looks like my mother. This is my mother, but it's not her. Aliens abducted her, and they replaced it with this dummy. What happens is, yes, it is your mother. It looks exactly like your mother, but you don't have the feeling of familiarity, the warmth that is associated with perceiving your mother. So all these alien abduction stories, well, some of them are based on this syndrome. So then they asked, is there a module in the brain for face recognition? Okay, and here you see the fusiform face area, the fusiform gyrus, so to speak, which is, shows quite a bit of activity for faces. Now, one interesting study is done with Mooney faces. Now, look at these images. Can you see the faces in the images? When you're looking at these images and you're not perceiving a face, there is no activity in your fusiform gyrus. As soon as you perceive the face, there will be activity, well, simultaneously. That means this processing is happening at some higher level than your basic visual perception, right? And then it's a cognitive function, right? And once you perceive one of these faces, there is no going back. You will always see the face. So, is there anybody who hasn't seen one of these faces?
I can't see
This one?
the
Okay, the eyes, the nose, the mouth, the chin, the ear, the hair. Can you see it now? The eyes. I think it should be enough, but the mouth. Yes, I spoiled this for you forever. Now, every time you look at this image, you will see the face. So this is another evidence for face-specific processing. Because as soon as you realize it's a face, something different is going on in your brain. But is this all? No, this is not all. There is also another thing that is specific to faces. When we perceive faces, we perceive them in a holistic way. What do I mean by that? I mean that you perceive the face in its entirety. There are some features that you derive from the entire face, as opposed to from the parts of the face. Okay, how can I tell this? An experiment to show this is that I show you a nose, and I ask you to identify the nose for me. For instance, I show you the nose of Obama. And you can do this with some accuracy. But then I show you the nose in a context of a generic face, in an average face. And then you can do this better. Okay? So the external features are not from Obama. So they contain no information as regards with discrimination. But that your performance increases means that there are some holistic features that you're extracting from the whole face. Okay, as if you're doing a PCA on the whole face. Actually, PCA coefficients are like the most typical holistic features used in facial expression, well, face analysis. So some groups try to measure this through different experiments. Okay, one thing that also tells you that there is holistic processing is that when I take the face upside down, your recognition accuracy drops greatly. Because turning upside down the face kind of disturbs your holistic processing. The feature-based processing, since it has rotational invariance usually, is less affected. And finally, I think the most striking proof is that you perceive this as a face. But this is just a circle, a few lines, and that's it. So that means you have a holistic processing, right? Now, there was this wonderful experiment done by Thomson in 1980, the Thatcher illusion. Thomson showed people this image of Thatcher, and people didn't realize there was something wrong with it until he turned it upside down. You see, what's going on here is that people are doing local processing, and the holistic processing is disturbed by the fact that the image is upside down. Okay? Now, but the local features are rotation invariant to some degree. So you don't notice that these are rotated 180 degrees. So you don't perceive this monstrosity. By the way, it's called Thatcherization now. Greatly unfair, I know, but if you Thatcherize the face, this is what you do. You should take the mouth and the eyes and you invert them.
It's being recorded.
I said unfair, didn't I? Okay, so a group in Max Planck Institute in Tübingen, Bültow's group, they did a very ingenious experiment to understand how much of face perception is holistic and how much of it is feature-based. They took a face, they measured your recognition accuracy, like not yours, but a group of subjects. Then they cut the face into pieces, shuffled the pieces, and they asked again, who's this person? And they measured the recognition accuracy again. Of course, it drops a lot. But then they start blurring these images until it drops to chance level. And then they say, look, we have introduced a blur, so much so that the feature-based processing no longer works. If we apply this blur back to the original face, we will find the contribution of the holistic part. because we have eliminated feature-based processing. Okay? So this is how they approached trying to separate the contribution of local-based and holistic face. And apparently, they are both there. So we have two routes of processing faces. Now, this becomes especially important for expression recognition because some of the things we look in expressions are really very subtle. I'm going to show you a couple of examples later. But there were people also, contesting this. For instance, Gautier and Tar, they trained people to recognize these little objects called greebles. Their hypothesis was that humans are face experts. We see millions of faces, so we become experts. And one of the most important things about becoming an expert is that your representation of the thing changes, right? Chess master, for instance, looks at the chessboard. He recognizes patterns, formations, offensive or defensive formations. But a novice will see only pieces. So the chess master has a much more efficient representation of a valid chess position. And that was their argument. They said, okay, the fusiform area, nice. It's for expertise, not for faces. And we are face experts, that's why you get activation. So what they did show was, okay, they took people, they showed them faces, they got the activation in the fusiform area, they showed them other objects, no activation, and then they showed them greebles for which they were trained, they were greeble experts, and there you have your activation. Okay? And then in an ingenious study, Gary Cottrell and his students created a neural network model for the fusiform area. They trained the neural network for doing intra-category classification, like separating cans from cups from greebles, as opposed to expert-level categorization, which means you're basically magnifying the small differences, right? If you're doing category level, that means you have to classify all sorts of weird chairs into the class chair. So you have to neglect their little differences. But if you're doing expert level classification, you have a lot of objects that are very similar to each other, and you have to separate them. So then they show that actually, if you train a neural network for expert level classification, and then you cut this part off and take the hidden layer and train it on a completely different expert level task, like chair separation, then that network generalizes much faster. So actually you can have a neural model of expertise to magnify small differences. And this is the kind of thing we need in emotional expression recognition. We need to magnify the small differences. This is a study that I was unable to replicate with my kid from 77, Maltzoff and Moore. They said that facial expression recognition is the key to communication. And babies are born with some capabilities of face processing that allows the baby to imitate the facial expression. So this is, of course, relevant for the dichotomy of whether face recognition is generic object recognition or not. If this is innate, then that means you cannot just take a random classifier, train it on faces, and expect it to work human level. You have to build in face-specific structures into your models, because we have those models, structures. The face recognition capacity of children changes in time. First, they start learning prominent features, like the hair, for instance, is very important. If the mother changes the hairstyle, the baby is stressed, because he or she no longer can reliably identify the mother, and that they have shown. But as the child matures, holistic perception becomes more important, and we learn that the hair is not so important anymore. So if you take an adult and measure the adult's face recognition or expression classification capabilities, the adult will disregard the hair. But if you formulate it as a generic pattern recognition problem, the hair has a lot of pixels in it, and it will be very salient, right? So you will see in the literature a lot of databases, a lot of results with cropped face area. This is the reason, you know. As soon as you treat the whole thing as a generic problem, the hair will get in the way. Okay. I'll move on to face processing in computers. Any questions with regards to face processing in humans? All right. Who knows what this is, what this frame is from? Which movie? Come on, you're all computer scientists. You should know this one. Yes,
Yeah.
perfect. Oops. This is the Voigt-Kampff test. Harrison Ford, you know, depicted as a shadow here, is giving the. Who knows Blade Runner? Who has seen Blade Runner? Okay. Who has read the book Do Androids Dream of Electric Sheep? Okay, less. All right. Anyway, in Blade Runner, we live in a time when the technology is really advanced, so we can create androids that really look human, really act human, and it's very difficult to tell that they're actually robots. And this guy is trying to give this robot a test to understand whether he or she is a robot or not. And the test involves measuring emotional responses. So he's looking at, for instance, the pupil dilation in response to some queries. Like he tells the robot, no, you know, you just smashed the head of the baby with a mace. And then he observes, is there any dilation in the pupil? But you see what's going on here? Our aim is to create systems that can show emotions. Our aim is also to create systems that can diagnose these things, right? So the Voigt-Kampff test is, of course, in a far, far future. We have more pragmatic reasons for achieving this technology, but this has been a dream for a very long time. And facial expression recognition for computers is precisely difficult from the reasons which makes face recognition in general make difficult. So you have pose variations, you have illumination variance, you have session variance, like, you know, this is acquired like 1 month later, and some things change. The hair changes, the clothing changes. The resolution can be very low or very high. And then you have the expressions, you know, that changes the appearance. Now, as a, you know, simple and naive from a naive perspective, this is difficult for a computer because all these are the same person, but the pixel values are completely different, right? Here you have a lot of high-valued pixels here. Here you have a lot of low-valued pixels here, and this portion. So if I take my face under illumination A and your face under illumination A, that will look very similar, as opposed to switching illuminations. So you have to construct specific embeddings, specific manifolds, in which the variation does not correspond to illumination changes, but to identity changes for recognition and expression changes for expression recognition. Okay, so I actually talked about this slide a little bit more than I wanted to in the beginning, so I'm going to skip this. You know what the pipeline looks like for the computer system, and it starts with transforming the face into a representation that is suitable for doing the analysis of the face. And what happens is that you need to select good features, as in almost all pattern recognition problems. And the kind of transformations that you impose on the face can be biologically motivated. You can, you know, try to understand what is it that makes humans such good face analysis systems, and then try to implement this in computers. Or you can, you know, discard these cognitive or psychologically motivated models and, you know, go with statistics. You can say, look, I don't know the models, but I have data. Let the data drive my models. So these are like two different approaches. And in general, if you want to do human behavior analysis, this is what you do. You either have models motivated by some external knowledge, like from sociology, from psychology, etc., or you take a data-driven approach. And sometimes some unexpected domains give you the best model for modeling some behavior. Like if you're going to model the behavior of crowds moving through a metro station, fluid dynamics, as it happens, gives you the best models. So you may find your models in different disciplines. I'm going to give you a couple of examples of biologically motivated models. Okay, so I have given you a few examples of how humans process faces. Now, our visual system implements some filters that are particularly suitable for face processing. And time and again, it has been shown that Gabor wavelets, for instance, are very useful for doing face analysis. Then you have this holistic as opposed to feature-based distinction, and there has been approaches like the eigenfaces and the accompanying face space hypothesis that is inspired by the biology, but also features and how they relate to each other. The structural information was embedded in some earlier models like the elastic bunch graph model. And then we have also fantastic illumination compensation abilities. You know, if you're wearing, let's say, glasses tinted with a reddish color, actually you will see everything in tones of red, but you will still perceive the colors, right? You will still know what's blue and what's green. And this is due to your fantastic visual system, which kind of cognitively does, which processes color in a higher level than the lowest level of receptors. So we can get some inspiration from that. This is the Gabor filter. It's basically a Gaussian convolved with a sinusoidal. And if you change the frequency of the sinusoidal, you will be emphasizing high frequency or low frequency information on the faces. So I'm assuming that once you create this wavelet, you will convolve your face image with wavelet and get a representation. And by controlling the orientation of the sinusoidal and the frequency of the sinusoidal, this is roughly what you will be getting. The orientations will emphasize either horizontal or vertical features of the face. So if you want to do mouth processing, you will probably go to this orientation. And then the frequency will give you the fine or coarse information. And surprisingly, coarse information is sometimes more useful than the fine information. A generic face analysis system starts with face detection. Face tracking relates to this. Then you have feature extraction, and these can be actually simultaneously done, as in active appearance models, for instance. Then you have either recognition, but you can also have emotion recognition, gaze estimation, behaviors that are useful for human-computer interaction would also fall under this part. Face detection, the state-of-the-art, well, there are many more face detection systems at the moment, but Viola Jones is really easy to use because OpenCV has this one-line code that lets you retrieve the face box from an image, and that has ensured that Viola Jones is used everywhere now. It's a cascaded classifiers of simple features, which has a second benefit. The cascade rejects most of the facial areas as not being, well, not most of the image early on. So it looks at a part of the image, it says, nah, this is too uniform to be a face, it discards it. And once suspicious of the existence of a face, it goes to the second level, third level, etc. So that's very rapid, right? It rejects like 60% of the facial area, the image areas in its first stage. The 5 features of the second level, 80% of false positives are rejected. Very nice. But you should understand that this is, you know, the model itself is easy to understand in a mathematical way. But if you want to actually go ahead and train a system like this, then you need 10,000 non-faces, 5,000 faces. So you need a lot of annotated data. And the OpenCV comes with a cascade for face detection and another one for eye detection, which is also used a lot. Is it perfect? No, it's not perfect. When the Viola-Jones gives you a face boundary, it doesn't give you always the nicest boundary, and it's not, you cannot just, you know, take two Viola-Jones bounding boxes and align two faces. They won't match. There will be slight variations in the bounding box. So even if you have found the faces, aligning the faces cannot be done directly after face detection. You need some more specific processing for that. And you will have, you know, missing faces or false positives. You know, this is detected as face. Usually illumination is a bane of all face processing, so you need to have illumination compensation, histogram equalization, anisotropic smoothing, manipulation of DCT coefficients in log domain. These are some of the techniques that have been traditionally used for dealing with illumination. If you have very good transformations that you have learned from your training data, specifically eliminating illumination, that can also be possible. Or you can use feature transforms that are resistant to illumination effects. Local binary patterns have been found to be really successful in this manner. So here you see the same face acquired under different illumination conditions, and you look at the LBP representation, they are very similar. What you do here is you encode a certain pixel by its difference from the surrounding pixels. Okay? People also now extend this idea to the spatiotemporal domain. I don't know whether Ivan gave you examples of that, but you can also create LBPs in 3 dimensions. If you create a spatiotemporal cube, then this point can be the center of your cube, and then you can look at the neighborhood in the 3 dimensions to compute an LBP descriptor. And that will give you basically a little bit of temporal information along with spatial information. Fernando actually mentioned the face space. Let me show you one face space. This is where we assume that there is a transformation, there is an embedding, in this case onto 2 dimensions, where once you transform your faces, then nearby examples are meaningfully related to each other. And if you follow, let's say, a trajectory on this space, you also obtain a meaningful transformation. So you can, for instance, transform a smiling face to a frowning face, or you can change the rotation of the face. Now, this is obviously nice if you want to do synthesis, right? If you want to synthesize an emotion, if you can construct a space like this, then you can take this, you know, you can take one point here and go in this direction and see what happens to your face. Obviously, if you go too far, it will be distorted and you won't get meaningful results. But this way, you can get some expressions that were not in your training set. Okay? And if you find a good transformation from, let's say, my face, and then you take, let's say, somebody else's face and you project it to this space, then you can move in this space from that point on and then expect similar outcomes. Now, okay, the eigenface method is basically doing PCA on faces. Fernando showed you how to do this, but I'll just very quickly go over it. It's what he called the snapshot method. Because this is a very classical problem that you will face when you're doing face processing. You will have 10,000 dimensional objects, and you will have only 100 of them. So if you want to do covariance matrix you will have 10,000 by 10,000 covariance, which is not full rank, and you will not be able to invert the covariance matrix. So how do we do eigenphase? How do we compute the eigenvectors? Well, this is actually also in Ivan's slides. I'll just go over it once more. You have a covariance matrix, which is, so n is the number of samples, d is the number of dimensions, and d is really high. So this is 10,000 by 10,000. Now, the eigenvector decomposition of this is basically you multiply S with an eigenvector, and then you get an eigenvalue times eigenvector. So this is the equality. And we're looking for V here. Now, okay, S is D times D is too big. Now, suppose we look at, instead of T transpose T, we look at TT transpose, which is N by N. So if I have 100 samples, this is a 100 by 100 matrix, which is manageable. What is the eigenvector decomposition of TT prime? Is TT prime U equals lambda 2 U. I multiply both sides with T prime, and I rewrite both sides. This is a scalar, so I can take it in front of it. And what do I get? T prime T is basically S. And here I have a vector. Here I have the same vector, and here I have lambda. That means this is actually the eigenvalue decomposition of S. Okay? So this idea was introduced by Kirovich and Sirovich and Kirby, but used by Turk and Pentland as well. And this is the famous eigenphase method. If you do your PCA analysis, you take some images and do your analysis. This is the first eigenvector, second, third, so they look like faces. And as you see, they encode, the first ones encode illumination. This encodes illumination from top. This encodes frontal illumination. And identity or expressions, those will come in much later actually. So your intuition of taking the first big eigenvalued eigenvectors would not work for expression recognition. You need to look at eigenvectors with small eigenvalues. But then you have LDA or Laplacian-based transformations that don't quite produce face-like vectors. But still, you know, if you use all of them and you use a coefficient matrix, you can reconstruct any sample in that high-dimensional space. Now, a nice thing that you can do with this kind of transformation is image-based shaving. So I can remove your beard by doing some transformations with this method. Can you imagine how I would do that? So suppose you have learned the eigenvectors and eigenvalue transformation. What it does is, it's basically an encoding, right? So you're representing the face, let's say, in a smaller dimensional space. Let's say I'm talking about 10,000 dimensional features. Let's say you go to a 10-dimensional eigenvector space. You will be retaining maybe 95% of the variance. 5% you will be losing. How would you use this to lose the beard, for instance? Well, you can train you can find your subspace from images that do not have beards. Then this variation will not be properly encoded in your eigenvectors. So when you go to the subspace and when you come back, since those dimensions are not encoded, they will be lost in transition, right? So this is how these people can remove the beard. Similarly, you can find the eigenspace from people without glasses, and when you go to this subspace and come back, you will be losing the glasses. Okay, if you don't do this with the same background, you will be also losing some things from the background, but that's a different story, right? Here, basically what they're doing is they're just using the face area in the projection and back. Okay. So that's how we use PCA, basically. The second very influential model in early face processing research was the elastic bunch graph model, which said the following. Okay, we have some facial features, like mouth corners, nose tip, eye corners. We want to learn models that retain the relationships between these features. So in the elastic bunch graph, you assume that these features exist in a certain relationship to each other, which you represent as a graph. And it's an elastic graph, so you can actually deform the graph. You can take two nodes apart from each other, but it's elastic. So the more you take them apart, the more resistance it will show. So this will penalize large distances between adjacent features. Plus, you will have one set of features encoding each local feature. So if this is the mouth corner point, then I will have its location to other mouth points. So its distance is encoded. But I will also model the appearance of this local feature with a Gabor jet. A jet means I have filters in a number of directions and a number of scales for this small local neighborhood. And then when you're trying to fit this model on a face, you will be optimizing basically two terms. First term, coming from each point, the local appearance of that point should look okay. So you have a jet similarity measure here. It should look like the jets that are in your database, in your gallery, let's say. Plus, the graph should be kind of reasonably looking. Okay? So when you do pose changes, you transform the whole graph instead of just a single point. A very similar idea is the active appearance model, which uses many more landmarks, okay, maybe 60 to 120 landmarks, depending on the model that you're using. And the shape of the face is encoded as a vector, as a vector of coordinates, landmark coordinates, so x, y coordinates. You can do this also in 3D, in which case you will need x, y, z coordinates, right? And then the fitting of this is in an iterative manner. Suppose this is the original image. You start with fitting a generic face, an average face, and you synthesize from the positions of the landmarks and from the appearance of the landmarks. So you will have two terms, one shape term and one appearance term. You will synthesize, and each time you will fix one, optimize the other, and then fix the other, optimize the first one. And then at the convergence, basically your shape and appearance vectors will be encoding the closest combination of your basis vectors. There are a few variants, okay? At active shape models, models textures of small neighborhoods around the landmarks and iteratively minimizes the distance between the points and models. The active appearance model looks at the texture in the convex hull of the landmarks, so it looks at a region, and it synthesizes the face, as I've shown you. Constrained local model does the same thing with AAM, but it models local patches instead of the whole face. And then Milborough and Nichols recently implemented an extended active shape model, which proposed several variations, like selectively using landmark profiles instead of one-dimensional landmark profiles, stacking multiple active shape models, using more landmarks, trimming the covariance matrix, so doing some. So these are all hacks in a sense, but it works good. Then it can track your face, and it can give some good results. Here is an example of face tracking, just to show Fernando doing a funny gesture here. Here you have the active appearance model fit on the first frame, and then you can track each feature, so you can actually update your model incrementally. You don't have to solve the whole thing at each frame, right? So you fit it once, and then you track. That's nice. Now, who knows here the morphable models? Okay, Very few people. So I'm going to show you a video. It's an impressive result that veteran Blance showed at SIGGRAPH quite a few years ago. But let me see whether I can get this going. Okay. How do I get this to be full? Ah, okay.
The morphable face model is derived from a dataset of 200 colored 3D scans of faces. Individual faces are combined into a single morphable model by computing dense point-to-point correspondences to a reference face. A modified optic flow algorithm establishes 3D correspondence automatically. The morphable model combines 3D shape and texture information of all example faces into one vector space of faces. We can form arbitrary linear combinations of the examples and generate continuous transitions.
This is again very much like PCA, okay? So you're basically
Starting from the
basis
average
vectors.
face, individual original faces are caricatured by increasing their distance from the average.
So you're increasing the coefficient of one of the basis functions, the basis vectors.
Forming the average for male and female faces separately, the difference can be added to or subtracted from an individual face to change the perceived gender. Other facial attributes, such as the fullness of a face, can be manipulated in a similar way.
You can
From
learn
a
any
labeled
kind
set of
transformation
faces,
from
the
it.
characteristic changes are extracted automatically. In our model, they're controlled by a single parameter. Differences in facial expressions captured from another face can be mapped to any individual.
It's not as good as it's shown here, actually. So when you actually implement it.
We now reconstruct 3D shape and texture in order to animate a face, given only a single photograph of a person. First, we manually align the average face to the target image, roughly estimating position, size, orientation, and illumination.
So since this is a complex optimization problem, it has to
Then
start
a
from a
fully
very good
automated
initial point.
algorithm finds the best reconstruction of the face within the morphable model. 3D shape and texture are optimized along with parameters such as size, orientation, and color contrast. The output is a high-resolution 3D mesh of the face. It is an estimate of 3D shape and surface colors based on a single image. Additional texture extraction improves details in texture. The reconstruction can now be rendered into the image, and a whole range of facial variations can be applied. Here we simulate weight gain and weight loss. Facial expression can be post-processed in images, forcing a face to frown or to smile. From this image, we also estimated 3D shape and texture and combined the photograph with 3D computer graphics. Cast shadows of novel objects are rendered correctly into the scene. Illumination conditions can be changed, and pose can be varied to some extent. From a single black and white image, we obtain a full estimate of 3D shape. The result of the matching procedure includes an estimate of surface color, since the morphable model contains color information. Finally, we show the application of our model to a painting.
Okay. Well, that should give you an idea about the morphable models. Let's continue with this. So this is how the texture actually looks like in the morphable model. It's like if somebody flayed your skin and made it into a shape and texture vector, parameterized by cylindrical coordinates, and then you combine the shape and texture in an additive way. This kind of shows you what you can do if you have 3D information. And in Vision, for instance, there was a lot of work trying to extract 2D information, 3D information from a single image. And the way it is made possible by morphable models is that when you have a lot of training phases, you can learn appropriate projections, which then can be meaningfully representing 3D variations. But of course, you need detailed 3D representations. Okay. So I come to the part of the talk where I talk a little bit about the 3D modality. 3D has been made popular in face analysis quite recently, actually. There were some collected 3D databases, but the 3D sensors are pretty expensive, and they're more difficult to control. So they didn't become that popular. But now we have somewhat cheaper sensors in 3D, and there was since September 11 there was a lot of work in biometrics, and 3D face biometrics became suddenly more important. So there was a lot of work, novel work done on this modality. The advantage of having a 3D information is you can have rotation and pose correction, and you can also deal with illumination if you're able to render, if you are able to synthesize new faces. The disadvantage is that the acquisition devices are usually expensive. There is a lot of noise, and we don't know how to adequately represent the 3D objects. It's not like, it's a bit more complicated object than 2D. So this is Kevin Boyer, who collected the FRGC, the Face Recognition Grand Challenge dataset, which was the first large 3D dataset with a clearly defined protocol and challenge. So how do we characterize this face? Well, we can represent it as a point cloud, like a bunch of points in the 3D space, x, y, z coordinates. Then we have some methods that can do alignment given 2 point clouds, because registration is still a problem. But typically, a high-resolution scanner will give you 30,000 points. So here we have a lot of points on the face surface. Another representation is surface normals. Okay? A lot of points and the associated surface normals. That's more informative than the point cloud, but you can have too many normals depending on the resolution of your surface. You can represent the face by a set of profile curves, simple line equations. And you can do matching with them. It's a kind of like a sparse representation. It's easy to compare, it's easy to calculate, but it's not fully descriptive. You're losing a lot of information. You can use curvature. A curvature indicates whether a point is on a surface which is concave or convex. But computation of curvature is problematic. It's very sensitive to noise. So you have to apply a lot of processing, smoothing, which kind of loses the discriminative information. Then you can use depth images, which is a 2.5D representation. You basically say, okay, I'm going to treat this as a 2D image. The points closer to camera will have high intensity. The points further away from the camera will have low intensity. That means you can almost use all the methods developed for 2D face processing directly on 3D images, because you're actually representing them as images, which makes it simple. And finally, most of the 3D sensors acquired the 2D image on the process, so you will have texture information. And that means most 3D methods are not just 3D, but the fusion of 2D and 3D is available to you as soon as you move to 3D. By the way, shall I give a break at some point, or?
I guess so. We need a coffee, right?
Okay.
So, are they bringing the things? Ilya, are they bringing the coffee and the...
Okay, okay. So just for your information, I'm going to be talking about, I'm going to be giving some examples from the Bosphorus database, which I have with me. So if anybody wants to use this database, it's a 3D database of facial expression. I'm authorized to give it to you. It's a bit big, I think something like 6 gigabytes. But I can also leave a copy with Jose, and then you can grab it later. That database contains 105 subjects and about 4,600 images, up to 35 expressions per subject, fax scoring by 2 independent fax encoders. 1/3 of the subjects are professional actors and actresses who are posing for expressions. There are systematic head pose variations, a variety of occlusions, beard, mustache, hair, hand, and eyeglasses. And we acquired it with a 3D structured light scanner at one of the interfaces. It was in 2007 in Istanbul. So this is the kind of occlusions that you will be seeing in this database. And the annotations, the landmark annotations, are also in the database. That basically concluded my part for 3D. But
let me make this clear, because I didn't understand. You mean that you have permission for
yes.
students to use
yes.
the database?
No, they can take it away.
Okay,
so
they have to sign.
I'm going to take their names, and Bülent Sankur will give them a blanket permission, basically. So. Yeah, so the second part of the talk will be on registration and landmarking, and then applications of. So it's best I stop here.
So let me